Hello friends, welcome to another new video on quantum mechanics, quantum theory of hydrogen atom, wave equation for hydrogen atom, and we're gonna complete this topic in one video because I don't want to make this I don't want to explain this topic in several videos because without continuity it is difficult to understand, so video gonna be long. Okay, so be patient. And this is my Insta ID. If you want to follow me on Insta, OJHALAKHYJIT123. And before we start, please do subscribe to the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you, and I help you to grow my channel. So now let's start. So you see, the hydrogen atom is a system of two particles. One is proton and another is electron. Okay, bounded by electrostatic force, and charge of electron is minus E, and that of proton is plus E. We have taken like that. And in absence of external electric field, the electrostatic potential energy of this system of two particles, that is, one is positive E, another is negative E. That potential energy of this system is given by this expression, right? I will explain how we have got this equation number 1. And here let me write the meaning of epsilon naught, that is permittivity of free space. R is the distance between the electron and proton, okay, in this case, and this is charge of proton, right? So hope you have understood this. So now you see, for a system of two charges, suppose one charge is capital Q, another charge is small q. Q is the source charge and small q is the test charge, and between them there is a separation, that is R. And in that case, potential energy of this system is given by capital Q into small q by 4 pi epsilon naught R. So here we have replaced the capital N small q by plus E and minus E, and that's how we have obtained this expression, right? Hope you have understood this. So now let me go to the next slide. Okay, so here you see the time independent Schrodinger equation. Let me write the time independent Schrodinger equation, that is given by here. Let me take one more, let me say one more thing. Let me tell you, proton is taken as stationary here because it is much heavier than electron, that is almost 1836 times heavier than electron. Okay, so that's why proton is taken to be stationary, at rest relative to the electron. So that's why here we have written the Schrodinger equation for electron is given by this. This is suppose equation number 2. Okay, so here V is the potential energy we have talked about in the previous slide. So here you see what we're going to do now. Let me write the meaning of the symbols that I have used in this equation. Okay, these are the symbols, meaning of the symbols. Let me write here. Okay, so this is Laplacian operator, and this is Laplacian operator. This is in Cartesian coordinate. Then I'm gonna use in polar coordinate to obtain the polar form of the equation number 2, the polar form of the Schrodinger equation. So these are the coordinate system. This is the Cartesian coordinate, and in this system the position of electron is this. Okay, this is the position of electron. X comma y comma z is the coordinate, and O is the position of this origin, is the position of the proton. Suppose I have kept that proton at the origin. So let me draw the perpendiculars here, projections from this projection of this electron on the planes. So here you see this is x and y. Okay, now here I have taken this angle is phi, this angle is theta, and this is r. This side is r. Okay, so this is perpendicular. Okay, so now you see, from this system, if you write this in polar coordinates, then x coordinate gonna be equal to this, and y coordinate gonna be equal to this, then z gonna be equal to this, right? And phi will be a function of these three polar coordinates, right? So now you see, let me explain how we have got this. So here you see, first take this right angle triangle, this right angle triangle. So here you see this triangle, this is Z, this is R, this is theta, right? Okay, and from this triangle you see this is the perpendicular, this is the hypotenuse, and this is the base. We can consider that way. And sine theta is equal to perpendicular by hypotenuse P by R. So perpendicular will be equal to R sine theta. So this perpendicular is nothing but this one. Here you can see, and this is this line and these two lines are equal and parallel. Okay, so it is difficult to draw perfectly in 2D. To draw a 3-dimension picture, it becomes very difficult to draw a 3-dimensional 3D figure on 2D plane. So though here these two are here we have to consider, though it is these are not seen like parallel, but we have to take these two sides as parallel and equal. Okay, so if this side, this perpendicular is R sine theta, then this side is also R sine theta. This is also R sine theta. Okay, so hope you have understood this. Now you see this Z coordinate will be equal to, you see, from this triangle, Z is the base here, so we're going to take cos. Okay, so let me clean this. Cos theta, that's going to be Z by R, so Z is equal to R cos theta. That's what we have got. Now you see, now let me clean this, and here you see this triangle is on XY plane. So here from this triangle, this is perpendicular, this is the Y coordinate, this is Y coordinate, that means this is Y. The coordinate of X, Y, Z, the coordinate of electron is X, Y, Z. So here you see, so this must be X and this must be Y. Okay, now you see this is the angle phi, this is the angle phi here. Let me just write here, this is angle phi. Okay, let me write it properly. And this side is your R sine theta. Okay, this is perpendicular and this is hypotenuse. So sine phi will be perpendicular, that is Y, by hypotenuse R sine theta. So that's why Y coordinate is equal to R sine theta into sine phi. So this is what we have got. This is the Y coordinate, right? Similarly, let's find the X coordinate. How to obtain the X coordinate? This is X, right? This is X, this is X, that's why this is X. Okay, so here you see we're going to take cos phi, which is base by hypotenuse, so that is X by R sine theta, and that's why X is equal to R sine theta cos phi. So hope you have understood this. So in this coordinate system, that Laplacian operator will be of this form. Let me go to the next slide. Here you see, so this is going to be the Laplacian operator in polar form. So how we have got that, that's going to be a different topic, so we are not going to discuss in this video, otherwise it's going to be very long. It is already very long. Okay, so now you see, just give me a second. So if we use this polar form, okay, if we use this polar form, in this we replace this Laplacian operator by its polar form. This is the polar form of the Laplacian operator. Then what are we gonna get? Just replace this by this polar form. Okay, then from equation, so using the polar form of Laplacian operator in 2, we have got this. Okay, so then equation 2 will be of this form. So is the equation, let me write. Okay, this is suppose equation number 3. Okay, now this is the polar form of the Schrodinger equation. Okay, this is the polar form of the Schrodinger equation. Okay, now we can express this wave function phi, which is a function of r, theta and phi, all the three, as product of two functions, and one is function of small r. Capital R is function of small r, then capital Y is function of theta and phi. So here this is the function of r only, this is the function of theta and phi both. Okay, so if we use this in equation number 3, then that means using 4 in equation number 3, we have got this form. Okay, so I will explain how we have got this. Okay, just let me write the equation first. Okay, here is the equation. Okay, this is what we have got, right? And so here let me tell you one more thing. So now this phi is replaced by r into y. Okay, so r is the function of small r, this y is the function of theta and phi. So now you see, since this r is a function of small r only, r is a function of small r only, this r is a function of small r only, and here we have differential coefficient with respect to r. So y is not function of r, it is function of theta and phi. So these are independent variables, r and phi, theta, all. So that's why this y is taken outside. So that's why I have written this y, and I have kept this r here. This is r. Okay, and as this is independent variable r, so that's why we can write the ordinary derivative here instead of partial. But here this y, you see, when you have replaced this function phi by r into y, and r is function of r only, so that's why it is taken outside, and phi is function of not phi, y is function of both theta and phi. That's why here we can't use the ordinary derivative, right? So here we have got two variables, so that's why we have to kept as partial. Okay, so hope you have understood this. What is the reason behind writing the ordinary derivative? Okay, so hope you have understood this. Okay, so that's how we have got this equation. So now what we're gonna do here, so let me show you. So now let us divide. So here ey, okay, we have replaced this psi by ry, not ey, sorry, ery. So there is already e, then psi is replaced by ry. Okay, so now let us divide both sides by yr or ry, and then multiply this term. Okay, so that's what we're gonna have. So doing so, what we're gonna have now, you see, so if we divide this term by y and r, so y will be cancelled, so we're gonna end up getting here 1 by r, right? Hope you have understood this. So then again, if we divide this y by r, then r will be cancelled, so we're gonna get y here. Okay, so hope you have understood this. Then similarly here also, if you divide this by yr, then r will be cancelled, we end up getting 1 by y here. So similarly you can divide this one by also ry, this one by also ry. Okay, and then if you multiply this with this, then definitely 2m will be cancelled, minus plus, h cut will be cancelled, right? So we're gonna get r square here. That's what we're gonna have. So hope you have understood all these things. So doing so, what we're gonna get, let me write on the next slide. Okay, let me go to the next slide. Just give me a second, let me clean this first so that you can note it properly. So let me write what we have got after simplification. Okay, so we have got this equation. So this is what we have got. Okay, so let me write here. So now let me simplify this equation also. So we can simplify this way. So what we are doing here, we have multiplied this r square with this term within the square bracket. So here r square will be cancelled, and so here also r square will be cancelled. This r square will be also cancelled. Okay, and so on. So hope you have understood this. So now let me write what I have got after simplifying this equation. Okay, this is suppose equation number 5. So don't be confused with this. So this is v of r means simply v. Okay, so because it depends on the r, small r, so that's why I have written v of r. Okay, that's it. So now here you see it has two parts. This equation has two parts. One part depends on r only. This first part here you can see it depends on r only, and the remaining part, this remaining part depends on theta and phi both. Okay, right. So each of them must be a constant, because this part and this part, these two parts are independent. Okay, so this part doesn't depend on this and this part doesn't depend on that. So that's why to get equal to 0 on right hand side of the equal sign, to get 0, so both of them must be constant. If this is plus m, then that must be minus m. You can consider it that way. If it is plus m squared, that must be minus m squared. So then it will be possible to get 0 on the other side. Okay, now let me go to the next slide. So one part of this equation, and this is the next part of the equation. So let me go to the next slide. Okay, so here you see, so let us consider the first part, which is the which depends on r only, that is equal to this l into l plus 1, and the remaining part, let it be 6, equation number 6, and the remaining part of the equation that depends on phi and theta, let that be minus l into l plus 1. So why I have considered these two? Now you see, let me go back to the previous slide, just give me a second. So here you see what we have got here, that I have told you that this is the first part and this is depends on small r only, and this is the next part, second part, which depends on theta and phi. The reason behind considering that each of them is equal to l into l plus 1 and l minus l into l plus 1, as we have written here, because you see this l is, you know, orbital angular momentum quantum number, orbital angular momentum quantum number, and angular momentum operator. Okay, angular momentum operator, when it's operate on this harmonic function, so that means we are talking about this part, second part, which is a function of phi and theta. Okay, when it operates on this function, okay, then this l into l plus 1 will be the eigenvalue. Okay, will be the eigenvalue of this function, this operator. So we have considered, instead of considering other constant, we have considered this constant. Okay, so if you don't have the idea of this operator, eigenvalue, eigenfunction, then don't think about it too much for the time being. Just remember the reason behind the considering, why I have considered this constant, each part constant equal to l into l plus 1, because this is the region. Okay, so here is the eigenvalue of this operation, when this l square is the angular momentum operator, when it operates on this function of phi and theta, so it gives l into l plus 1, then again this function. So one more thing I forgot to write here. It should be written this way. Just give me a second. There should be an h cut. Okay, So that's why we have considered the functions this way. So as we are to get 0 here, that's why we have taken positive, this part is equal to this positive constant, and second part we have considered the same constant but negative. So both are equal and opposite, then only it is possible to get 0 here. That is the reason behind that, considering this way. We have considered the same constant but opposite in sign, right? Hope you have understood this. Now you see equation number 7 can be solved by again variable separation method. So if we consider this function of phi and theta as a product of again two functions y1 and y2, which are function of theta and phi, okay, which are independent, okay. In that case, this equation number 7 can be replaced this way, can be written this way. Let me write this. Just give me a second. Here I think I have made a mistake. That this is supposed to be sin theta, okay, sin theta. So here what we have done here, this y is replaced by y1 and y2. So here we have differential coefficient with respect to theta, so that's why y1 is function of theta, so that's why we have kept y1 here, and this y2 is taken outside, that will be cancelled by this, right? So hope you have understood this. And similarly we're gonna do the same thing here as well, okay. And now here you see y1 and y2 are functions of theta and phi only. This y1 is function of theta and y2 is function of phi only. Here we can use the ordinary derivative as well. So let me write here, we can use the ordinary derivative also this way. Let me simplify this equation, okay. So what I have done, we have multiplied this term with this term within the curved bracket, then we have multiplied each side by sine square theta, and after that we have got this equation. So now you see, so this equation is here, you see, consists two parts, okay. So now you see what are those two parts. So let me write here, I missed something here, just to give me a second. So here you see this part, you see, is function of theta only, okay. This is one part, and next part is, this is function of phi only, okay. This is the second part, and sum of these two parts is equal to 0, and this is gonna be possible if both of them, each of them is constant, and those constants are equal and opposite, then only this condition is possible. So let me take the first one as plus m, and the second part as minus m, plus m square minus m square. Let me take that way, okay. Let me go to the new slide and let me write that thing. So this is what we have considered, m square, and this is minus m square, where m is orbital magnetic quantum number, okay. We're gonna discuss about the quantum numbers later, not now, in another video, okay. So now here you see, this can be written this way if we simplify, right? And solution of this equation we have got is equal to this. Solution, general solution of this kind of differential equation is given by this, right? And it can be written this way. There's a reason behind it, because you see, if you check the coordinate system, x, y, z, this was z, this is y, and this was the point position of electron, and this angle was phi as I have considered. Now you see, if you change this angle by 2 pi, then again you're gonna reach the same position, right? So here is the angle phi. If you advance it by 2 pi, again you're gonna get the same position. So that's why we can write this way, right? Hope you have understood this. So again we know that here you see, if we put this here, then what are we gonna get? Let me write the region here. Okay. So now you see, from y2 is equal to e to the power I m phi, what we have got? We have got this, because this y2 is a function of phi. When it is function of phi, we get e to the power I m phi, and when y2, we're gonna write y2 of phi plus 2 pi. y2 of this means, so this phi should be replaced by this. That's it. So hope you have understood this. So that's why on the other side we have got this. Now you see, we can write this way. Okay, this can be written this way. Hope you have understood. Now these two cancels, so we have got this. Now if we cancel these two, we're gonna get this is equal to 1, right? And here you see, let me tell you one thing. So how we have got this relation? Because e to the power I theta is equal to cos theta plus I sin theta. So we have used this relation to obtain this relation. Okay, hope you have understood this. Instead of theta, we have this. Okay, and we know sine 2 pi m for integer m, it is always equal to 0. So that's why we're gonna end up getting, so first let me write this is equal to 0 for some integer m. So that's why we left with this result. And general solution of this equation, this cos 2 pi m is equal to 1, means here you see, if you put m is equal to 0, plus 1, minus 1, plus 2, minus 2, for all those values of m equal to integer, we will get here 1. Okay, that's why here m is equal to 0, plus minus 1, plus minus 2, dot dot dot, so on, right? Hope you have understood this. Okay, because we know this the general solution of this cos x is equal to 1, then x is equal to 2n pi. We know this relation, n is equal to plus minus 0, plus minus 1, plus minus 2, dot dot, so on. That's why here this m must be equal to 0, plus minus 1, plus minus 2, dot dot dot, so on. So hope you have understood this. Now let me take a new slide. So what we have done here, the radial equation that we have obtained in the last slide, let me write the radial equation. So here is the radial equation that we have got. Before considering this, let me write something. So here is the radial equation. Radial equation means, let me go back to the previous slide. Here you see this equation number 6. Here you see, this is the radial equation. Okay, it depends on r only. So now you see, let us consider, so now let us consider this u r is equal to r into capital R of small r. Okay, so we have introduced a new function. So u of r is equal to r into capital R. Okay, so if we simplify this, then what we're gonna get, r is equal to u by r. So when we say r, that means r of small r. Okay, we are not writing every time this, right? Hope you have understood this. Similarly, when we are writing u means u of small r. We are not going to write all the time. So if we differentiate both sides with respect to r, then we're gonna get this, right? Using the u by v rule of derivative. Then if we simplify this, then what we're gonna get, So this is what we're gonna have. So now let us differentiate both sides with respect to r again, then we're gonna get this if we differentiate both, right? So I hope you I don't need to explain this. So here I have used the product rule, r into this first function derivative of second function derivative of first, that means derivative of r is simply 1. Okay, so here these two will be cancelled, so that's what we have got, right? So we have understood this. Now using this results in the above equation, in the radial equation, so we're gonna get this, the above equation becomes of this form. Okay, so that means here we have replaced this by this result, sorry, this whole thing, this part by this result. Okay, hope you have understood this. Then r is replaced by u by r smaller. Okay, and so on, and this r is also replaced. Okay, that's how we have got this. So now let me simplify this. So after simplification, instead of v of r I am writing simply v now. Okay, that's it. So that's what we have got. What we have done, we have multiplied both sides by this term. Okay, so there must be h cut square. Okay, I forgot to write the square, so h cut square. So here is the equation. This is equation number 8, suppose. Okay, now you see, let us take k is equal to this. Now you see here, this E is negative. Total energy for bound system is negative. Remember that for the time being, because here in this system we have got negative potential energy, and potential energy is for bound system potential energy is more than kinetic energy, so that's why total energy will be negative, so that k remains real number. Okay, so it is a bound system, so that's why here total energy remain total energy E must be negative here. Okay, so that k is a real number, because you see, if this E is positive, then this term within the under the root will be negative, so in that case k will be imaginary. So this, if E is negative, then it will be real, right? And for bound system, E must be negative, right? So let me write this one. Potential energy of this system was this. We have already I have already mentioned earlier, this was the potential energy, right? Hope you have understood this. Okay, so now you see, let me go to the new slide. So let's see what we get. Now you see, from this relation we can obtain E. We're going to write this expression in terms E is equal to something, whatever we get from this relation. Then we are going to divide this equation number 8 by 9. What was the equation number 9? Let me go back to the previous slide. Equation number 9, where I have written, so I forgot to write, I think. Okay, you see, sorry, we will write the equation number 9 from the expression we're gonna get from this result actually. So let me go to the next slide. Okay, so this was the expression we have considered, k is equal to this, and from here we're gonna get E is equal to this, right? So this is suppose equation number 1. Now let us divide equation number 8 that we have obtained in the previous slide, and by equation number 1 dividing 8 by 1, 9, not by 1, by 9, we're gonna get this relation, right? So hope you have understood this. So again, let me write potential energy is equal to this. Okay, so now here you see, let me simplify this. Okay, this is what we have got, right? Now suppose this rho is equal to k into r, and rho naught is equal to this part. So here we have taken this as rho naught, okay, not this one only, this part, okay. Hope you have understood this, so that this above equation becomes of this form, right? So then here you see, let me explain now. This is suppose equation number 10. Let me write this equation number 10. So what we have done here, so this was equation number 8. Here you can see this is the equation number 8, right? This is the equation number 8, and from this expression k is equal to this, from this expression we have obtained equation number 9, and we have divided this equation number 8 by equation number 9. So but what we have done, we have divided this right hand side by the left hand side. So that means you can write this equation number 9 first. Before you divide, you have to write this equation number 9 in this way. You have to write the left hand side on right hand side, and right hand side on left hand side. So E on this side, okay. So now this equation, divide this equation number 8 by this equation. So dividing 8 by equation number 9, we have got this result, okay. And now let me proceed further. So here you see this k square r is written k into kr, and this part we have taken rho naught, okay, rho naught, and here you see we have taken kr is rho, so that's why this middle term becomes rho naught by rho, right? Similarly, this kr square will be rho square, as we have taken kr is rho, right? Hope you have understood this. This is very simple simplification. Okay, now you see we're going to examine the asymptotic behavior of this solution. So asymptotic behavior means a function, if a function grows with if its variable tends to infinity, and it grows up to very large value, there is no any certain point that up to this point that function will grow, then that is asymptotic. So first we're going to check the solution for rho tends to alpha, okay. Then equation 10 will be of this form. So here we have to examine the asymptotic form of solution. So general solution of this equation will be of this form. So now let me explain here. You see, if rho tends to infinity, then you see these two terms will be 0. Anything divided by infinity will be 0. That's why in that equation we're gonna get 1 into u here on the right hand side. So that's why this equation takes this form, right? Hope you have understood this. So now you see, so asymptotic behavior, here I have written to examine the asymptotic form of solution. So what do you mean by asymptotic? When you see if you have a function and if you draw its graph, suppose, and suppose let me consider here a function of rho, suppose, okay. If when rho tends to infinity, okay, this is the values for rho, suppose this axis, and when it tends to infinity, its value be suppose if you suppose it graphs is like this. Suppose here you see, suppose we have a line here that such that this on as rho tends to infinity, this graph approaches to this red line but never touch this red line, okay. Then this is called asymptote, and this behavior is called asymptotic behavior. So that's why to examine that we have to take that take this condition that rho tends to infinity, right? So now here you see, as rho tends to infinity, e to the power infinity is 0. That's why this equation, this solution u of rho, that will be equal to a to the power a into e to the power minus rho, because e to the power plus rho is infinity, then it's gonna be 0. So that's why second term is 0. So on the other hand, if rho tends to 0, so here I supposed to write rho tends to 0. In that case, this term become dominant here in this equation number 10. See, here when this rho tends to 0, right? So anything divided by 0 is infinity, and so here you see, if you put 0 here, this is going to be the greatest largest term, and that's going to be dominant over the other terms, so we can ignore the remaining terms, and then this equation 10 can be written in this form. Let me take a new slide. Okay, let me take a new slide. So this can be written this way. Okay, and its general solution will be of this form. Okay, so now let me go back to the previous slide again to explain this. Okay, so here you see, if this term is dominant, you can ignore these two terms, so then this equation will be of this form. Okay, right? Now you see, before going to that equation, let me explain the meaning of asymptote again. Suppose if you have a function f of rho, suppose, and if you draw a graph for its for this function, and you see that if this axis represents rho, if rho represents tends to infinity, and its graph suppose approaches towards a particular line, but it never touches that line, then this is called asymptotic behavior. Okay, so hope you have understood this clearly, that what is asymptote. Okay, so now let's go back to this equation. Let me go to the next slide where I have written this equation. Okay, so this is the equation number 10, as rho tends to 0. Okay, and general solution is of this form. Okay, so where I have taken this form, I will explain it. First let me write, as rho tends to 0. Now let me come back to this condition. If rho tends to 0, then this equation will be equal to approximately this, c rho to the power l plus 1, because rho to the power minus l, that's gonna be that's going to be negligible. Okay, right? So now you see, this rho tending towards 0. Now you see, as rho tends to 0, this part going to be very large, infinitely large, and that means the function is not defined at that point, so we're gonna ignore this second term of this solution. Okay, so hope you have understood this. Now you see, for a small rho, let us introduce a new function, that is v of rho. So such that u of rho is equal to rho to the power l plus 1 into e to the power minus rho, then v of rho. Okay, so here I am using cursive v instead of the bold v that was used for the potential energy. So now we're going to use the cursive v for this. So here you see, if we differentiate this with respect to rho, both sides of the above equation, then we're going to end up getting this result, right? Now what we have done here, you can see that clearly. So there are three functions, this one, right? here we're going to use the product rule. So first let me write again, let me rearrange the terms and taking commons. We have got this. Now again, if we differentiate, we're going to get this result. So here you see, so these are the three functions. If we differentiate three functions u, v, w, then how to differentiate it? First we differentiate u, okay, then we keep the other two terms, then plus again, then we're gonna differentiate v, again the remaining two terms, then again at the end we're gonna differentiate the last term. So hope you know this rule of derivative. Okay, so that is what we have done here. So product of three functions. So first we have differentiate this term here, we have got this one, and remaining two functions are this. Then similarly next time here we have differentiate this to get this one, and there is minus 1 also. Then at the end we have differentiated this v of rho. Okay, then we have taken this term common and we have got this. So again here you can consider this one as function product of three different functions. Okay, so then again if you apply this rule, then you're gonna end up getting this result. Let me show you. So you're gonna end up getting this result. Okay, that's what you're gonna have. So here you see, first we have kept these two as it is, then but I have differentiated this part. Okay, so here you see again you can apply here the product rule, u into v, that rule. So we have kept the first function as it is, then we have differentiated this, then again we have differentiated this part. Here differentiating this part we have got 1 into v, this one, right? So hope you have understood. Differentiate this, derivative of L will be 0, derivative of 1 will be 0, derivative of rho with respect to rho is 1, but there is minus, so it's going to be minus 1. So we into v, that's why we have got minus v here. So hope you have understood this. Then in this bracket again we have two terms. Okay, first take the product of these two. First differentiate this. If you differentiate this, you will get 1 into dv by d rho. Then keep the second function, first function, then differentiate the second function. Here we're going to get second order derivative, right? Hope you have understood this. Then again, as derivative of this part is done, so then again what we have done, we have written this part as it is, then we have differentiated this function. So that's why we have got this one here. Then we have kept this function as it is here. So then after this part, so we have done with these two parts. We have differentiated this one and this one. Now we have this one. If you differentiate this, then you will get this, so this term. Okay, then here also we have used this same rule. Okay, then if you simplify this, then you will get this. Okay, I'm not gonna explain each and every term of simplification. Okay, I hope you will understand. I have explained how I have differentiated this. So let me write the steps of simplification. These are the steps. So how we have simplified this. So let me write all the steps what we have done. So let me write. Okay, so okay, then the final equation will be of this form. So let me write that one too. So that's what we're gonna have. Okay, so that's what we have got, right? So we're gonna use this this result in equation number 10. And let me tell you one more thing. I have forgot one more thing to explain. Just let me go back to the previous slide to explain that. So here you see I forgot to explain how we have got why we have taken this general solution of this form. Okay, so actually I don't think I need to explain this kind of things here. This is differential equation. Okay, so hope you have got the idea of differential equation. But okay, let me explain this one as well, why I have taken this equation, taken this solution, general solution of this form here. So let me explain here. Okay, so now you see this equation here, it is considered that this solution u is equal to rho to the power r. Okay, rho to the power r. Now if you differentiate it with respect to rho, then you're gonna get r into rho to the power r minus 1, right? And if you differentiate it again, then what you gonna get? If you take the second order derivative here, then you will get r into r minus 1 rho to the power r minus 2. That's what you're gonna have, right? Now you see, if we use this results in this differential equation, then what we're gonna get? Then we're gonna get r into r minus 1 rho to the power r minus 2. So this is equal to this one, right? And on the other side, we're gonna get L into L plus 1 by rho square. Instead of u, we're gonna write this, okay, rho to the power r. And if you divide this rho to the power r by rho to the power p, then you're gonna end up getting rho to the power r minus 2 here. Okay, and this rho to the power r minus 2 rho to the power r minus 2 cancels, and then you end up getting this equation. This is the quadratic equation. Okay, so here this implies that L square plus L minus r into r minus 1 is equal to 0. And if you solve this quadratic equation, you're gonna get two roots. One is L plus 1, another is minus L. So that's why we have taken here this solution of this form C, rho to the power L plus 1 and rho to the power L minus L. That's it. Hope you have understood these things. Now let me go to the next slide again. So what we have got this. Now using this result that we have got in equation number 10, if we use this result in equation number 10, where is the equation number 10? Let me go back to the previous slide. This is equation number 10. If we use this instead of this, if we use this result here, you see that's what we have got in equation number 10. Then what we're gonna get? Now let me go to the next slide. Let me write here. So equation number 10 will be of this form. Okay, so let me simplify this. Right, after simplification we have got this is equation number 11. Okay, so now you see, so what we have done here in equation number 10. So let me go back to the previous slide, just give me a second. So how we have obtained this? We have put this value of second order derivative of u with respect to rho. So let me tell you one more thing, this should be v, okay, not u, this time second order derivative of v. Okay, so we have used this result in this equation number 10. Here is the equation number 10. So this is the equation number 10. Here we have used that value, second order derivative of u with respect to rho. So and this u also, this u is replaced by this function that we have considered, that u is equal to what we have considered. U is equal to rho to the power L plus 1 e to the power minus rho v of rho. We have replaced this u by that value. So which one we have considered here? Here you can see this one, this value. Okay, so instead of u we have written this value in this equation number 10, and instead of second order derivative of u with respect to rho, we have written this result. Okay, so hope you have understood this, and doing so we have got this result. Okay, so hope you have understood this. Okay, So this is the value of u that we have put here, and this is the value of this second order derivative of u with respect to t. Okay, so now you see, let me proceed further. So this v of rho can be expressed as power series in rho. So here we're going to use the power series solution method, that is Frobenius method. Okay, so here we're going to consider this solution of this form, right? So then if you differentiate it with respect to rho both sides, then you're going to end up getting this. Okay, so that's what we're going to have. Then if let me replace the j by j plus 1. I will explain what is the reason behind it. Okay, replacing j by j plus 1, we have got this, right? So I will explain it. Just negative power, to avoid the negative power on rho, so I will explain it. So again, differentiate it both sides with respect to rho, then we're going to end up getting this. So now let us use these results in equation 11. So now you see, so let me explain why I have used here, instead of j, I have replaced this by j plus 1. Because you see, if you put this, if you use this in this equation number 11, so for j equal to 0, you're gonna get rho to the power minus 1. Okay, so then in that case, this the mathematical operation is going to be very complicated. So that's why, to avoid these circumstances, I have replaced this j by j minus j plus 1. And here you may think that here also we have got rho to the power j minus 1, then why we haven't replaced here j plus 1 by something else? Because you see, when you will put this value here, there is already one rho, and when it will be multiplied with this, then it's going to be plus j, right? That's why in this case we don't need to replace. But here you see, in this term there is no other row here, so that if we multiply here, we're gonna get this okay, rho to the power j instead of minus j minus 1. Okay, so hope you have understood this. So now let me go back to the previous next slide. Actually what happens, we're gonna multiply this with this row and this one as well. When you will multiply with this row, then you will get rho to the power j. Okay, but in this term there is no row here. You're gonna end up getting if you use this one, you're gonna end up getting rho to the power minus 1 if you put j is equal to 0. That's right. So in order to avoid that, we have to replace this j by j plus 1. As simple as that. So now let's go to the next slide. Okay, so from equation 11, now using this new function after using this solution as power series. So what we can do, first let me write the equation number 11 as it is, how we have got in the previous slide. This was the equation number 11 we have got in the previous slide. So I have written the equation number 11 as it is. You don't need to repeat it because I don't want to go back to the previous slide again. So that's why I have written the equation number 11 again. And what are the results we have obtained? Let me write those two. Okay, these are the results we have obtained that we are going to use in equation number 11. Okay, so let me just give me a second. Okay, so actually what we have done here, so I have written this equation number 11 and these two results, this one and this one. Okay, now let me copy this equation number 11 and this results. Del u by del rho is equal to this one, and second order derivative of del v, first order derivative of v with respect to rho is equal to this one. Let me copy this result, and second order derivative of v with respect to rho, and equation number 11. Let me copy these three equations and let me write in the next slide so that I don't need to come back to the same slide again. Okay, so here you see This is equation number 11, and other two results which are going to be used in this equation. Okay, this value is used here, and this value is to be used here, and using those values in this equation, we're going to end up getting this result. Let me write that. Okay, right, that's what we're going to have. Okay, so this V is replaced by this result that we have considered. Okay, we have considered that solution is equal to this, right, power series solution. So now you see here what we're gonna do. So let me tell you one more thing here. So here you can see clearly we have replaced this by this result, and if you split these two terms like this, 2 into L plus 1 and minus 2 into rho, and if you multiply this its result, this result, okay, then you should get here rho to the power j plus 1. Okay, but here what I have done here, you see, as already we have a rho here that we can multiply, so we haven't used this same result in this part. Okay, so here you see this is multiplied with this part and this part, and when we have multiplied this del v by del rho with this part, 2 into L plus 1 into del v by del rho, so we have used this result that I have given here, and this result was obtained by this like this way. Actually we had got let me go back to the previous slide. Here you can see first we had got this result, right? Initially we had got del v by del r, del v by del r, sorry not r, del rho is equal to summation j is equal to 0 to infinity j c j rho to the power j minus 1. Okay, we have replaced this j minus 1, sorry, j by j plus 1 to avoid the negative power on rho. Okay, if you put j equal to 0, then you will get negative power, so that's why we have to avoid that. So but here you see, let me go to the new slide again. Here we had here you see input in this result, here we had used this result, this one, here you can see we have used this result. So this is replaced by this result, summation j is equal to 0 to infinity j plus 1 into c j plus 1 rho j minus 1. Right, now you see what we have done, that initially we had this result del rho by del v by del rho is equal to j is equal to 0, summation j is equal to 0 to infinity j c j plus 1 and rho to the power j minus 1. Now here you see, look at this part, 2p into 2p not p, sorry, rho, 2 rho into del v by del rho. As here we have already one rho, so we can use this result here directly, because when you will multiply this one with this, then you will get simply rho to the power j. That is what we have written here. Okay, so now let us equate the coefficient of rho to the power j equal to 0. Okay, let me equate that so equating the coefficient of rho to the power j equal to 0 means, so here you see in this equation on the right hand side we have 0, that means you can consider 0 into rho to the power j, so here coefficient is 0. So on the left hand side, what are the coefficients of zeros, coefficients of rho to the power j, those can be equal to 0. Okay, so equating the coefficients equal to 0, we will get j plus 1, c j plus 1 plus 2 into L plus 1 j plus 1, then Cj plus 1 minus 2j Cj plus rho naught minus 2 L plus 1 Cj is equal to 0. So these are the coefficients of rho to the power j, right? Okay, so we have written the coefficients of rho to the power j here and equating to equal to 0. Now if we simplify this, then we will get this term, right? This is suppose equation number 12. Okay, now you see, for a large j, so as we are going to examine the asymptotic behavior, so we have to take large j, which corresponds to the large value of rho. So if j is very large, in that case we can ignore the remaining terms other than j. We can ignore this part, because j is itself very large, right? So that's why we're gonna end up getting this, right? And if you cancel j and j, then we're gonna get this. Okay, right? Now for j is equal to 0, we will get C1 is equal to 2C0 if you put j is equal to 0 here in this equation, right? Then if we put j is equal to 1, then C2 will be 2 by 2 into C1, and C1, as we have already got that 2C0, if we replace the C1 by 2C0, we're gonna get this kind of result. Similarly, we can put j is equal to 2, j is equal to 3, so we're gonna end up getting these results. Here you can see, right? Okay, now C2 will be equal to, that can be written here. You see, 2 square divided by 2, which 2 means 2 into 1, that can be factorial 2, right? Similarly, this result you can see 2 cube, C3 can be written as 2 cube, 2 cube, right? Hope you have understood this. And divided by 2 into 3 into 2 into 1, that means factorial 3, so it can be written in this way, right? So similarly, the other two terms also, this one can also be written as 2 to the power 1 C0. This C1 can be written as 2 to the power 1 C0 by factorial 1, and this one, that C4, can be written as 2 to the power 4 by 4 factorial 4. Okay, so now you see, that's how we can write Cj is equal to 2 to the power j by factorial j C0, right? So what we're gonna do here now, V rho, that's gonna be equal to this, right? We have considered the power series solution. This, okay, we have already considered earlier. This is the power series solution of this V, value of V. So now you see, what we're going to do, we're going to use this result here. So then using this result instead of Cj, okay, we will get this solution, and this implies, so here you see, so how we have got e to the power 2 rho. Actually what happens, this summation you can see here, if you expand e to the power x, you will get this kind of result, right? This is the expansion of e to the power x, and instead of x, suppose if you have e to the power 2 rho, then the expansion gonna be like this. This one gonna be the expansion. Okay, now if you observe this expansion carefully, then you can write this in this way using summation, right? If you put j equal to 0, then you will get the first term. If you put j is equal to 1, you will get the second term, and so on, right? This can be written this way. So that's why here you can see, we have replaced this part by this one. Okay, this part is replaced by this e to the power 2p, which is the expansion of 2p. Sorry, e to the power 2p, not only 2p. So this is the positive exponent, okay, exponential, and it is asymptotic. We know that when rho tends to infinity, then e to the power 2 rho, that's going to be e to the power infinity, that goes to infinity again. Okay, so that means it is asymptotic. We are not going to get a particular value that for which we're going to get so if for rho tends to infinity, we're never going to get a particular value. It goes exponential, right? This is asymptotic behavior because there is no specific limit to which this may grow when rho tends to infinity. And in such case, okay, so solution of radial equation will not be normalizable. Okay, hope you know the concept of normalization. You have already got in quantum mechanics, right? So hope you know this basic idea, what is normalization. I'm not going to explain here again. Okay, so there is only one way to escape that, if we consider that there must be some integer j plus 1 that must be equal to some number integer, that is suppose capital N, for which this series terminate. This series must terminate, right? So it cannot be infinitely growing series, right? So to have a normalizable solution, so that's why that's why the condition that should be satisfied for desirable result is there must be some integer n, which is nothing but j plus 1, like capital N, so that this term, you can say, let me go to the next slide, so that Cn, that means Cj plus 1, n means j plus 1, becomes Cn minus 1, and that means if you write n minus 1 instead of n minus 1, if you write j plus 1, that's going to be Cj, okay, if you replace this n by j plus 1, okay. So now you see this equation number 12 that we have got. Let me write the equation number 12 again. I don't want to go back to the previous slide again. So this was the equation number 12. So it implies that 2n plus L is equal to rho naught is equal to 0. That means here you see there must be some integer n, that is n is nothing but here j plus 1, for which this value is equal to 0. So if you put here 0, then and one more thing, if you put j plus 1 is equal to capital N, then you're going to end up getting this result, right? So this will be 0 into this denominator, that's going to be 0, right? So we end up getting this result. Now from here you see n plus L is equal to, let me take n small n, so that's why here we have taken this is small n, so that's why this equation is written in this way. So rho naught will be 2n, and we know that energy expression that we have already got in equation number 9 is given. This is equation number 9. I'm not going to previous slide, okay, we have already discussed. So if you have noted, then you can check equation number 9, okay. And also we have got these values, rho naught is equal to this, and from here we can obtain k, right? So let me do one thing, just once let me show the previous slide. So here you see this is the equation number 9, and these are the values we have considered. Rho is equal to this one, rho is equal to this, rho naught is equal to this one. I have written these two equations, this equation number 9 and this result again in this slide. Here you see. So here you see these are the results that I have written again, which are already we have written in previous slides, okay. So from here you can see we can replace this k using this result. Then we can put rho naught value here, value of rho naught, okay, that is 2n. Okay, so then what we're gonna get, equation number 9 will be equal to this. After putting the value of k, we're gonna get this equation after putting k. Now let's put rho naught is equal to 2n, then we're gonna get this. So here 2n whole square on it, then it can be simplified in this form. So hope you have understood this, what I have done. We know here you see we have whole square here, 4 square 16 to the 32. So here you see 2 square, that is 16, 4, 2 square 4, 4 is 32 again. Okay, so here we have e to the power e, I have written e to the power 2, then I have given here whole square, and here I have written 4 pi epsilon naught. Okay, and so I have taken 4 here only, 4 square 16, and here we have 2 square, here we have 2 square, this is a square, and 4 is 32, and here also you will get 2 and 16, that's gonna be 32. Okay, and here n square. So hope you have understood this simplification. This is very simple simplification, that being the student of graduation level, BSc level, you must understood this kind of things. So I don't think I need to explain this kind of things. Okay, so now let me make it clean, just wait. Okay, so here n is equal to 1 2 3 4 5 dot 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 so on. This is Bohr's equation, this is Bohr's equation, Bohr's formula. And at ground state, n is equal to 1, so if you put that, you will get this, right? That is approximately equal to minus 13.6 electron volt. And so En, this En can be expressed in terms of E1 like this. Okay, so because this part is nothing but E1, right? Here you see we have put that one. And yes, from this expression you can write the k in this way, that instead of rho naught, if you put 2n, then if you put 2n here, then you should get actually what you will get, here you see that 2 and that one, that's gonna be 4. Here we should not get n square, here we should get n only, not square. Okay, so then it can be written in this way, where a is equal to, just give me a second, this is only n, not n square, 1 by an, so a will be equal to this, right? So this is the radius, Bohr's radius. Okay, so hope you have understood this. Okay, so that's all for today. Thank you for watching. See you in the next video. Bye bye, take care.